something about the solution. This time we're going to use a warm solution. And so this solution, I let it get awfully hot. So it's actually at about 76 degrees Celsius. So let's put that in. All right. And so, hopefully I can pick that up. So we're going to put in another 20 milliliters of the solution A. And this solution A is quite warm. All right, so let's think about this. If our solution is warm, what do you think is going to happen to the rate of the reaction? Raise your hand if you think you have an idea. What do you think, Biz? What do you think is going to happen to the rate of the reaction?
I think it'll go faster.
Okay, so talk to me a little bit about why you think it'll be faster. Huh? What happens to particles when you heat them up?
They move around faster.
They move around faster, right. And so if particles are moving around faster, why would that cause the reaction to proceed more quickly? What do you think, Mason? Why do you think the reaction would have to proceed more quickly?
Isn't it when things get hot, like they expand?
What do you mean by expanding? The particles themselves blow up like
No,
that?
like
or?
they all like scatter out.
Okay.
More room to move, there's more room to move freely.
Well, we're not really changing the volume. So what does the energy actually make the particles do? Bump into each other. That's exactly right. In fact, the whole idea of chemical reactions is based on something called the collision theory. And in order for a chemical to react with another chemical, the atoms or molecules or even particles, we can say particles, have to collide. They have to bump into each other. So if you're moving around really fast, you're more likely to collide, right? Does that make sense? Okay, so let's test this. Now, we, at 21 degrees Celsius, our time was 7.5. So what do we think is going to happen to the time it takes for this to happen?
It'll decrease.
Okay, we think it might decrease. So because of that, we need to be ready with our timers, okay? So put your fingers on the yellow button. And I'm going to add, here we go, ready? Start. Stop. So how much time did it take?
6.02.
6 point.
Yeah, I got 6.
Let's go with 6.0. Okay. All right. So we definitely had a reduction in time. I was kind of thinking it might be a little faster than that, but that's okay. We definitely saw a reduction in our time there. All right. So that fits with our prediction. Let's go the other way. Also, I wanted you to notice we didn't have that layering out there. Why? I wonder why. Why do you think that didn't happen?
The density is
Because
closer.
they're moving so fast and they're so spread out that like it covers more surface area.
Okay.
And the density lightens up because they're going, or there's less density because they're going everywhere. They're like moving around.
Remember, density is actually a characteristic of the substance, so really the density is not going to change. So it's more a function of that particle motion, that there's more agitation or more motion in the particles, and so there's better mixing, basically, is what happened there, okay? All right, so now let's take a colder solution, which is over here on ice. This is right about 5 degrees Celsius. So this is quite cold. Remember that 0 degrees Celsius is freezing. So this is actually going to warm it up a little bit because the test tube's kind of warm. Try to get it out here fast. Okay. So that feels very cold. All right, so let's make a prediction. Our cold is at about 5 degrees Celsius. So what do you think is going to happen to the reaction time?
Increase.
Think it'll increase? You think it'll increase a lot or a little bit? Yeah, I said. Well, we think the time it takes to react, is that going to increase or decrease? That's going to increase, right? We're going to have more seconds tick off. So what do you think? It's going to be a lot more seconds? Just a few more seconds? Just a few, maybe? We didn't have a whole lot of a reduction when it was warm, so we'll see. So let's put in a little bit of our B. Once again, the B solution is the same every time. And it's got the starch in it, and I'm just putting in the same amount every time. Why do I have to do that? Why do I have to make sure the B solution is the same every time?
You can only test one variable.
Yeah, very good. You can only test one variable at a time. So we're testing our A variable. For right now, we're testing the temperature. Okay? All right, so here is our, so this is cold, so here we go. Ready? Got your fingers on the button?
Yeah.
And start. Top. So what was our time?
1.13.
11.
10.8, 11,
About 10.
10.7. Okay, so anybody get below 10? Anybody get below 10 and a half? Anybody get over 11? What'd you get?
11.88.
11.8, what'd you get?
12.
12, okay. All right, so why don't we just say 11, since we had a little bit of a range there. Okay, so that was actually quite a reduction, wasn't it? That cold temperature. Now, why did that happen? What happened? What do you think, Amara, with that cold temperature? Why did we have such a much longer time before we saw the change?
Well, because the molecules are not moving as fast as it was in, like, with the heat. So
Okay.
since it's cold, they're not going to be moving as much.
Okay, and so if they can't move as fast or as much, like you say, what can't they do in terms of the collision theory?
Bump into each other.
Right, they can't bump into each other. Okay, they can't bump into each other. Okay, very good. So we could actually talk about the relationship between the reaction time and temperature, right? Who could summarize that for me? Camera?
I actually have a question.
Sure.
Since that water is staying at that constant 5 degrees Celsius and it was moved to room temperature, wouldn't that have an effect on the reaction time?
Sure, and this temperature right here is probably not hugely accurate because you're right. I actually poured it into that graduated cylinder, which was kind of warm, and then it sat here for a few seconds. So this could be slightly warmer than 5. Probably if it was right at 5, this might have been even longer. Yeah, that's a good point though. And that's just something about experimental design that sometimes we have to think about that leads to a little bit of error in our results. And so that happens all the time in science. But that is a good pickup. Okay, also I think it's interesting to notice, look, here's the hot one and there's the cold one. See that? This one mixed all the way through, and this one you still have that layering out because of the cold temperature, the substance A and B aren't mixing quite as well as they did when the temperatures were hot. There's just not enough collisions, right? Okay, now let's talk about concentration. Because since we pretty much came up with, oh, actually we didn't do that because if you ask another question. So let me ask that question again. If you had to come up with a sort of a summarization of what we just saw here with how temperature affects the reaction time, what could you say? What would you say, Mia?
What?
If you had to make a summary of how temperature affects reaction time, what would you say?
That when it's warmer,
Mm-hmm.
that it's like moving, like the particles are moving faster, so it kind of like stirs it, so
Right.
it makes it faster. When it's colder, they slow down.
Okay.
So it takes longer for it to make some
Okay, good.
react together.
And okay, good. So, and I like how you kind of corrected yourself because like mixing and chemically combining are different things, and we kind of use those words interchangeably. But I just want to make sure that you understand that when we're talking about what's happening right here, they're not just mixing. There's like a chemical reaction happening that's producing this substance which turns blue, right? Okay. Okay, good. So now let's talk about concentration. Let's look back at our control. We had a 25% solution, and at that concentration, we had about a 7.5 second reaction time. So let's say that we double the concentration of your potassium iodate, solution. So that means that we've got half and half, right? What do you think is going to happen to the reaction time if we double the concentration? What do you think, Brian? If we double the concentration, so we're going from 25% solution to a 50% solution, what do you think might happen to the reaction time?
Increase.
You think it would increase?
Yeah.
So talk to me what you mean by that. Do you think more seconds would tick off or less seconds would tick off?
Less seconds.
Why?
Because there's more of that substance in there.
Okay, so there's more of it in there, and so what's more likely to happen? Okay, good. They're more likely to bump into each other. If you've ever been in an elevator, if there's only like 4 people on the elevator, where does everybody stand? In the corners, as far away as possible from everybody else on the elevator. But if there's a whole bunch of people in there, sometimes you can't help but like actually contact the person next to you, and it's all awkward and uncomfortable, right? But because there's an increase in concentration, we didn't change the size of the elevator. It's only because we put more people in there that you ended up touching or colliding. And so when we are increasing our temperature, increasing the concentration, we're increasing the likelihood that particles are going to bump into each other. So let's test it. So if we're going to double our concentration, what do you think? You said it'll decrease. Do you want to give a prediction about what the time might be?
Maybe 7 seconds.
Okay, so here at 25 we have 7.5. So you think if we double it, we're going to drop our time by a half a second?
Sure.
Maybe? Okay. Would anybody like to make another prediction?
I would say 4.5 seconds, maybe.
Why?
3.5 seconds, because if it's 25% and we got 7 seconds and you doubled it, so that means you're gonna like cut time by half.
Yeah.
So it would be 3.5 seconds.
Okay, that's really good thinking. So let's go with both of those. So you're thinking it probably isn't going to make a lot of difference, but you're kind of thinking like conceptually, even mathematically, like okay, if we double the concentration, maybe it's going to cut the time in half. So let's see what happens. Okay, so we need our 50% solution. That's this one. And this is at room temperature. So remember, we have gone back to holding the temperature constant relative to our control up here. And then we have to put in our 10 milliliters of the B solution, which is the same, remember? Okay, so we ready? Okay, get your fingers on the little yellow button. Ready, and start. Stop. So what did we see? What was it?
3.5.
3.5?
7.
3.7?
7.
Did you really get 7? No. What did you get? 4? 3.5? 4? Okay. So let's go with 3.75. Sounds like that would be a good average there. So it looks like your prediction, Sarah, was spot on. That when we doubled our concentration, that the reaction time was about cut in half. So let's make a prediction about when we reduce our concentration. So this concentration is actually half of our control. So I just reduce the concentration. We are at 25% with the control. I reduce it down to half. So let's try that one. Who would like to make a prediction?
Bet it's going to be like 12 seconds.
I think it's going to be doubled.
Okay. So you think it might double the time?
Yeah.
Okay.
Double more.
All right. So let's make a prediction. Let's see who can get closest. Okay.
Say 14.
Okay. Who's this?
14.
14. Okay. Just write down your prediction, just for the fun of it. We'll see who gets closest. All right. Okay. So we need our 12.5 solution. Make sure that I'm doing this right. That would be a real bummer if I didn't put the right solution in here. And then we're at our B solution. Whoops, it's a little too much of that. Okay. Okay, get your fingers on the yellow button and start. Stop. What did we get? 16.3. 16.3, 16.5 around. Did anybody get it right on?
No, I put 12.
12. Who? Anybody put 16? 15?
15.3.
15.3. What'd you get?
15.
15? Okay. Well, and that would have been exactly, I mean, the 15s, that's a good prediction because that would have been exactly the double. But, so our time was about 16 and a half. That's still pretty good. You guys made a pretty good prediction. So one of the things that I want you to understand about reactions and the reaction times, that it's predictable. That we can make predictions based on the variables that are happening during the reaction, whether it's temperature, whether it's concentration, those variables affect the speed of the reaction. So I want you to look down at, go ahead and go past, there's a little section there to write down the definition for temperature, the definition for concentration, and then also the collision theory. For the collision theory, all I want you to write there is that atoms, ions, or molecules must collide to cause a chemical reaction. All right? So the collision theory says that atoms, ions, or molecules must collide to cause a reaction. And what we did was look to see, well, how can we affect that? How can we affect that? So when we look back up at the learning target, can we predict how changing the temperature and concentration of reactants will affect the time? And so obviously we figured that we can. We did affect the time. So underneath the collision theory, there's two questions that I want you to answer. Question number 1 says that based on your results, to use the collision theory to explain how temperature affects the reaction time. Now, when you're asked to write something that includes a theory, what do you need to include in your answer? What would be some good words to use in your answer so that you're clearly using the theory to formulate your answer? What?
Colliding?
Yeah, that would be a good word. Make sure you use the word colliding in your answer so that it's clear you're using that theory. So I want you to answer that for number 1, and then I also want you to answer that for number 2. I'm going to give you a little bit of time, but I do want to hear a couple of responses.
Did you notice on the cold test tube it's starting to mix because it's going back to the
Right, yep. All right, would anybody like to share their answer to number 1? How did you use the collision theory? Yes, go ahead.
I said as you increase temperature of the solution, the particles collide at a faster rate, causing the rate of reaction to decrease.
Okay, good. So the speed of the reaction decreased. Very good. All right, I like that. So you did a really good job of incorporating that word colliding and using the theory to explain your answer. Okay? All right, so once you have that done, I want you to put this back in your binder because we're going to use it again tomorrow. All right? Okay, you can cut me off.